All right, so maybe we should get started in the interest of time. So our next speaker is Xue-Song Bai from Department of Energy Sciences at Lund University. So he's an expert on direct numerical simulations and combustion modeling and has worked extensively on premixed flames and diffusion flames also. So his current interests are in CFD modeling of NOx and soot and detailed combustion processes in internal combustion engines. And I think this is part of that. He's going to talk about direct numerical simulations of IC engines.
Thank you. Good morning, everyone. Thank you for inviting me to this excellent workshop. I'm going to talk about the DNS of a high-pressure machine. This is an IC engine. It's called a SACI engine. We have a research team here. Dr. Rixin Yu is the PhD doctor. He worked with me for many years from PhD study. And he's the one who developed the DNS code. And we have Henning Carlson, Fan Zhang. These are students that are working on using the code, applied code, working on different problems. I have the luck to work in Lund with many excellent researchers there. Marcus Adin yesterday presented the laser technique. It's excellent. We can use it to study many different things. Also there we have a group working on internal combustion engines. Ben Jorensson, some of you may know him. A leader group working on internal combustion engines there. I'm part of the research activity there. We are doing the modeling work. This is a slide I borrowed from Ben Jorensson. It's basically give an overview of the recent development in IC engines. We still run ICI engines and diesel engines. These engines are still there, but we have a challenge that we want to improve the efficiency and decrease the emissions. And there we have to do many things. For example, in the past many years, people has been working on something called the HCCI engine, which is a hybrid, in my opinion, diesel engine and ICI engine. There we try to use homogeneous mixture and compression ignition. So using the lean burn concept, so we can have high efficiency and low emissions. But we found that the control of this engine is problematic. You could have big cycle-to-cycle variations. So there has been a lot of experimental work going on there. Marcus' group was the one that used the laser technique to actually show that the HCCI engine is actually not a homogeneous process. There you have reaction fronts going on there. So a new development in that direction is something called the spark-assisted HCCI engine, which we call SACI, is the topic I'm going to talk today. SACI engine, especially in low load where ignition is not very favorable, there you can use the spark to start ignition, and then hopefully the premixed flame propagation can help the auto-ignition of the HCCI part. So this has been there for several years. There's also some problems there. Whether it's effective, the spark, fundamentally there is an issue there, ignition interacting with premixed flame. So it's an interesting scientific problem. Recently, we go one step further or one step backwards, depending on how you look at it. So we are working on the concept called a partially premixed combustion, compression ignition engine, which is the type of diesel engine we're using direct injection, but early injection, and then you form a partially premixed mixture. And I guess Dr. Karlovitz there, you are the one that showed using gasoline in this type of engine actually works very good. Gasoline in these engines works very good because it works in the TPC engine. So we have a small group there doing modeling, but we are asked to do modeling of these engines. which is actually mission impossible because the current models available are mostly for IC engines and diesel engines. For these complex engines, we need to go one step back to look at the fundamentals, how this engine combustion structure look like. Before that, we cannot say that we have a model which works for this type of engines. Okay, there's some problem. It's the internet. Okay, that's why this is a good motivation that we don't do the modeling as such. We go back to DNS studies. So we have a DNS code developed over a 3 or 4 years period. Thanks, John. You give a good introduction of this method. We read your paper. Actually, we did the same type of numerical methods. A little bit different thing is that we don't use this AMR, this local refinement. We use Cartesian grids, so we can do simple coding with high order schemes, and that we feel that we can easily do that, and then hopefully it gives more accurate results. So the work was finished in 2012. Since then, we have applied the code to many different things. One thing that doing DNS, especially for this transient process in engines, high pressure, is the initial condition. This is largely determine how good quality of your data is, because DNS cannot simulate the whole engine, so we have to really focus on small sugar cube domain in Jackie Chan's words. So that's very small compared to the engine. There the initial condition is an issue. Especially typically when one use synthetic turbulence to generate this initial turbulence, we have some development which we can have inhomogeneous turbulence. So the computation domain has been constant volume enclosure. This is the closest relevant to IC engines, constant volume enclosure. But we also develop a way based on the low Mach number formulation, the compression effect. The H term actually in John Bell's equation, the pressure equation there, you can include compression effect. So the code has been running up to 10,000 CPUs. It's a very good scaling in parallelization. So I want to give you first a few examples of this code application. The first example is actually the work that Jackie published some years ago, 2006. Yes. I know that Ian and Edward Hooks are co-authors of that work. I still have a question why you use a 4.1 millimeter domain. 4.1 is not a special, it's a very, very strange domain. It's not 4 millimeter, but 4.1. So what we did is, you guys did a 2D DNS. We want to say that this is HCCI type of work. So 2D DNS is okay. So our question is, how about 3D DNS? So we have a 3D code. We want to compare 2D DNS and 3D DNS to see if there's a big difference. I can tell you already now, qualitatively they do not. Qualitatively they may have some difference because 2D is 3D. But if you look at the statistical properties, they are very similar. So we using detailed chemistry from Dryas group. And here is the difference, the comparison. In 3D, one of the major discovery in Eva's work and Jackie Holmes' work is that you found that in HCCI you could have flame type of propagation and also ignition type of propagation. Flame propagation flame front propagate very slow, and ignition propagate very fast. So here the color is actually a coding whether it is a premixed flame or it is an ignition front. What we found that in 3D, of course, it's not a line anymore, it's a surface. Indeed, you have premixed front and you also have ignition front. Some differences in between 2D and 3D lies in that you have a curvature, 3D curvature, and also the evolution of turbulence and temperature stratification is a bit different, but that's all. So comparing the global properties, this mean displacement speed, we see a very rapid decrease from the beginning ignition, and then we see a flame propagation period, and then finally you have everything auto-ignite. So it burns very quickly at the end. And this is the evolution of the flame surface area. Sorry, this is the internet. 2D and 3D are actually differing a little bit. This is a statistical property, but we also test the grid dependence. Okay, in DNS we do have a grid dependence, but usually we cannot do a lot of grid refinement. For this case, we did that, and qualitatively they're okay. The next example I want to give you is the newest PPC concept. PPC engine works better than HCCI, but there is a trade-off between soot and NOx, ambient hydrocarbons. So the question is why? So engine experiments shows this behavior, but it's very difficult from engine experiments itself to understand why. So we did the simulation, it's 135 million degrees. We have to do a very small domain here because this is high pressure. High pressure, everything that, the reaction fronts become very thin. So you have to decrease, you have to increase your grid resolution and to allow for the heat release zone to have at least 20 degrees. So the heat release zone is 10 times smaller. So we have to decrease the grid size, the domain size by 10 times, basically. And otherwise, we have to have a 1,000 times bigger computer to do the work. So this was the case. We presented the work in the symposium last time, previous symposium. I want to just give you a short highlights of this work. Well, in short, what we found is actually in PPC engine, you have a HCCI type. This is from the early injection mixture. And there they runs like a HCCI. It's auto-ignition. This is HO2. You can see heat release rate. You have volume rate ignition process going on. But what is more interesting is that at the fuel rich is in the center part, we actually have very thin layers. It's almost like a flame there. So thin reaction zone. This is 20 microns, so it's very, very thin. You need to have 1 micron resolution to solve this problem. And you can see that the center reach, this is a PRF fuel. In the center reach part, it's not chemically inert. It's actually low temperature ignition is going on, which can be visualized using this HpHRc. As you can see here, initially at the edge of this fuel rich pocket, you have RO2, and then it's a volume rate ignition in the center fuel rich part. And then everything is converted to CO, carbon monoxide. And carbon monoxide, here is the bright zone carbon monoxide, is very hard to oxidize. And this is where the thin layer of the flame do the job. So you can imagine that the turbulence will play some big role in this type of engine. So even though it's a very small domain, we can learn a lot from that. And we also apply the solver to fundamental problem like turbulent flame interaction in inflow-outflow domain with a periodic boundary condition. John has shown some work in this direction. I think you are the first group doing this systematic change of Karlovitz numbers. We try to do that. So this is what we done with changing the Karlovitz number. I didn't show, we also have a Karlovitz number 1, that's a flame-led combustion. We didn't show that here, but we changed this. You can see that this is a little bit beyond the thin reaction regime of Norbert Peter's book. You see that still it looks like the heat release layer. This is heat release layer. This is the temperature distribution. You see that everything heat release occurs actually in thin layers. Even when you go to Karlovitz number 3000, it's not flame-light as such, but because you have some local inhomogeneous heat release, but still heat release occurs seems in thin layer. But you can see also the preheat zone, which is low temperature part, is becoming more complex. And the reaction layer is actually more twisted. So people say for high Karlovitz number, it's easy to model because you use worsted reactor. But actually, you have to be careful. There are more fine structure there. One of the work we discussed in this symposium paper is actually we found that elementary reactions play a big role in this type of flames. Imagine you have H radicals formed in the reaction zone. They are rapidly transported to the preheat zone. The time scale is so short. That is larger than the H radical recombination time scale. So therefore, there's a lot of heat release reactions, H plus O2 plus M, in this low temperature place, which is very interesting phenomenon. So in the next few minutes, I want to focus on the SACI. So I've been giving you examples. The SACI work is still under post-processing. We've done this work. In this type of engine, we found a very interesting phenomena. That is why I chose this flame. I want to discuss here. Before I go to the DNS work, I want to show that we did also the LES work. It's a real engine. This slides, I want to show you how SACI works. SACI, imagine you have a homogeneous mixture, homogeneous in mixture, but not homogeneous in temperature. So you put a spark, you put a flame, and this flame propagate and is highly twisted because of turbulence, flame interaction. But over the time, when the flame propagate, the charge in front of the flame can auto-ignite. I'm sorry that I didn't close this internet connection. You're going to have auto-ignition in the end. So we try to develop bravely a model based on flame-led for the propagation of the flame and also ignition, multi-zone type of ignition modeling for the mixture auto-ignition. In the flame-led model, you always have a problem, an issue of what is the displacement speed. If you use that as an input, then you're going to have problem because we don't know the structure of actually a SACI engine because we know premixed flame propagation, but in the ignition environment, this propagation can be strange. That's what I'm going to show you today. So we need to know the structure and propagation, flame ignition interaction. Flame ignition interaction exists also in diesel engines, lifted flames. They are in front of lift-off. You have a lot of low temperature chemistry going on there. So it's an issue of interest. Especially fuel types, how fuel types, different fuels behave differently indeed. So the goal of this type of investigation is not to simulate the engine, but actually to improve the understanding. Hopefully, based on this, we can develop runs and LES models. We have to still limit our domain to very, very small. I'm sorry for this very small domain. We need 1,000 times larger computer to do a sugar cube type of domain. So it's a 3D DNS. We have initially put turbulence there. It's a homogeneous mixture, even homogeneous in temperature to simplify the thing. We put a premixed spherical small flame in the center of the domain. And these are the setup. We have a pressure of 60 bar. Whether ideal gas law is working in this pressure, I hope it's working. Seems is okay based on Joe Alfanen's work. They did a lot of such type of supercritical fluid simulations. Seems still in this high pressure, high temperature condition, ideal gas can be useful. So these are the setup. We also did 1D simulations afterwards to improve to know the chemical process. So we use this same mechanism. And this is after very, very short time. This time is very small. It's deliberately made so because we increase the initial temperature to very high, so the ignition can be fast. So we'll be able to simulate the case. So next time it develops initially from a spherical homogeneous flame, it becomes a cellular type. We've seen in the lab yesterday, you visualize ignition process of rich isooctane, if I remember. There you see a lot of cells. This is probably a combination of hydrodynamic instability and diffusive thermal instability. In this case, we run hydrogen, so we have both effects. So next time it becomes this, and then like that. Afterwards, we don't have this structure because everything ignites. So before that, at this time, we can visualize the flame front structure color-coded with the heat release rate. You can see that it's very inhomogeneous in this type of flame. You have cusps, you have somewhere that the concave part or convex part, depending on how you look at it, you don't have heat release. And then in this convex part, you get a lot of heat release. And this, you can see here, the OH is not homogeneous. This is very typical cellular flame. It could be laminar flame. Laminar flame, you also have this type of behavior, which is due to differential diffusion. If we look at the evolution of OH in time, we can see that so far it's like a flame. It's a cellular flame. It's growing. And the reaction zone is very thin here. This is the OH layer. In the reaction zone, it's a super equilibrium OH, perhaps. And this is basically a post-flame zone. There, you still have OH. Now, the next time, you're going to have everywhere auto-ignite. It's just before the whole thing explodes. So we have a peculiar phenomena here. In front of the reaction front, just before the ignition, actually there is a very low OH layer. This very low OH layer did actually damage to the flame propagation. So here, I will quickly finish. Here I have want to show you the heat release rate. Everything is very thin, and suddenly you have a heat release in the end everywhere. And this is temperature, so everywhere you have. This is the initial turbulence. The turbulence field is destroyed by the expansion. So basically here probably we have a very low turbulent Reynolds number. We can do the flame speed analysis, which we saw that very rapidly you have a boost of flame propagation because flame becomes cellular, but then it actually decreases a little bit, the propagation speed. This is because of the OH layer, which is rather low in front of the flame. And we examined the structure of the flame by plotting the budget terms, diffusion, reaction term. They are comparable at an early time. So this means it's a flame propagation. At a later time, you have a very high reaction, but the same diffusion. So this is ignition driven at this moment. So quickly, we have, to understand why the OH has such a strange behavior, we did a lot of simulations with the different domain size and also temperature. We decrease temperature. We now simulate 1D, so we can do any temperature, even 800. And we can also do change of the diffusivity. We take away numerically the differential diffusion effect. And we found that you see that 1D, we also have this behavior, actually lower. And in this case, it's not lower. This is a larger domain. But the increase of the flame propagation speed is very low. We would expect that because of the heating is a constant volume configuration, the heating can increase the flame speed, but it does not. It's actually because of differential diffusion. We change this differential diffusion, it monotonically increases. Actually, it is a much faster propagation than, this is the same hydrogen, but we change deliberately the diffusion. The speed increases 10 times or increase much faster. So hydrogen diffusion destroyed the propagation. We plot the temperature here. Just before the ignition, we actually have a low temperature in this lower than the far-field ignition mixture. And we examined the main reason, actually, is because of differential diffusion itself. We have phi that is very low. This hydrogen is diffused to the burn zone in an early time. So we got a sink of hydrogen. And then we examined many elementary reactions. And here I show, I don't have time, so I go to summary. Eventually, we found that the main reason is because of differential diffusion first change the equivalence ratio in the preheat zone. And then that will affect the H radicals. The H radical recombination reaction in the preheat zone provide H2O2. And H2O2 provide OH in the end. So this process is actually slower in preheat zone than the far field. And that is why everything slows down. So by that, I finish here. Thank you.